let us look at the decision boundaries of neural networks and also some learned features. So neural networks typically make use of hidden layers. So here is one hidden layer neural network. So this is actually the logistic regression neural network we have seen in the last session, which has a linear combination of the input and a sigmoid activation function. For the output layer, it also uses a linear combination of the input followed by sigmoid activation function. And if we look at a degenerated case where there is zero hidden layers, there's no hidden layers, then the previous network becomes a linear classifier, such as this. And then the decision boundary becomes a hyperplane. So in two-dimensional space, it becomes a simple line. And here are some examples. And when we have just one hidden layer, the decision boundary is the boundary of a convex region. And in 2D space, it looks like this. So it is convex. And if we have two hidden layers, then the decision boundary we have are basically combinations of convex regions. And here are some examples. And if we have deeper neural networks, the decision boundary will become more complex. So let us look at some visual examples of the different levels of abstraction or different levels of features we can learn from a deep neural networks. And here, the hypothesis is that we don't know the right level of the abstraction because the problem is complex. So we let the model to figure it out by providing, for example, labeled data. And in the example of face recognition, deep networks can build up increasingly higher level abstraction, such as lines, paths, and regions. So here is a neural network with 3 hidden layers. So start with pixels. The first layer learn the edges, and the second layer learn the objective parts, such as eyes, nose, and eyebrows. So they are basically more complex than the edges, but they are just parts of objects. And in the third layer, we learn objects that look more like human faces. So these are different levels of abstraction, and with increased complexity when we go to higher layers. So let us look at the ingredients of this neural network in the standard structure. We know that to train a neural network, these are the typical procedures. Firstly, we look at the data. We need to sample a part of the data as batches. And then we do a forward pass through the network to generate some predictions. So this is basically apply our model to the batch data to generate some output. And then we will use a metric to evaluate the errors or the loss for this prediction. And then back propagate these errors so that we can update our network weights for a better prediction. So this is the optimization procedure. And here is a nice illustration of the training process for the digit classification problem. So here there are 10 units, 10 neurons for the 10 classes for digits. And basically, we need to do many iterations to to adjust, to update the weights so that we can achieve a good prediction accuracy. Therefore, for neural network, for the data, we still do standard pre-processing, but in batches. And the neural network, the structure or the architecture is basically layered networks of neurons. So basically, these are interconnected neurons formed in layers. And there are several hyperparameters to set. For example, the number of layers, how many layers to use in your neural network, and the number of neurons, or also called the number of units for each layer, except the input and output layer. And what activation function do we want to use? And for the parameters, we learn standard parameters for each layer. We learn the weights and the biases. And in terms of evaluation metric or the loss, it's also standard. We either use maximum likelihood, which is also equivalent to minimum negative log likelihood. And one of the most popular metric for classification is cross entropy. And for optimization, we use back propagation, which is gradient-based optimization method. So in the next two sessions, we will looking at the convolutional neural networks and how they operate and generate predictions.